It's great to be here and great to finally visit the place whose name is chanted most often at our basketball games. So I used the example of UMBC's miracle win over UVA a few years ago when I tried to teach Bayesian things, because never had a 16th ranked team ever beaten a first ranked team until they did. So, congratulations, awesome. We did go on to learn from that and do well the next year. So thank you for the lessons. But anyway, I love this venue. This is beautiful. And I love data science. It doesn't seem like work when you're doing the thing that you really enjoy. And the neat thing about having your own company is not having any bosses, because you have a lot of bosses. Every client, every employee. I have a wife, I got a lot of bosses. But you get to pick your own team. That's the really cool thing. And so finding people that are humble, but with little to be humble for, and work together well and really want to help the client. And then you have this technology that enables you to do so many awesome things. Like, we've helped discover drugs. We've done a lot of anti-fraud work, a lot of sort of spy work. It's called insider threat, for a lot of agencies, things like that. And you can get kind of you're feeling good about it, So this is kind of how we see ourselves, right? There's a dragon. Some group is facing some horrible dilemma that it's been terrorizing the village for 20 years, and you come in and save the day. And with extensive work with my clients, I realized they see us a little differently. Sort of like, hey guys, there's some good data over here, And anyway, it's a little bit of both. You got to do a lot of scrambling around in the leftover data. Nobody ever does controlled experiments for us and make life easy. We have to make a salad out of the weeds we find in the yard, We have to work with the data that's there for some other purpose. And it might be censored in some way. We could have survivor bias problems. So there's all sorts of I kind of like specialize on mistakes, having made a lot of them. So if you're interested in that, I can send you a book chapter I have on the top 10 data mining mistakes. It's kind of useful, a lot of stories in it. But today I want to focus on the positive end. I want to focus on kind of 3 aha moments in my career. A couple of them I developed, but then the third I'm just a student of. And those are the ensembles, the idea of combining competing models, and then target shuffling, which I really want to spend a little time on this morning because it's crucial. You've heard of overfit, but there's also the problem of oversearch. And in the process of looking at possibly millions or billions of modeling possibilities, a large part of your performance could be due to chance. So target shuffling is a way to create a simulated world where randomness rules, where the null hypothesis is true, and seeing how often your most interesting finding is more interesting than your real finding. Chance is always a hypothesis of how things could have occurred. So you just want to calculate and estimate how likely chance could have found, not that exact result, because that exact result is really interesting, but what made that result interesting? What was your metric that caught your attention that drew your eye to that result? Is there another, how easy is it to get something that interesting by chance? So that's probably the most important thing I want to talk about this morning. And then the huge problem in our field is that most projects don't get implemented. In fact, somewhere around 5 out of 6 projects that work in the lab industry-wide do not get implemented and used and start to return the wonderful 10x, kind of return on investment that they can. This is horrible, because why is that? Well, it's not so much the technology, it's more the people. It's the trust that people have to have. Why will people, the change management, why will they do something important in a new and different way? It's dangerous, it carries a lot of risk, perceived or not, real or not, it's perceived as incredibly risky. Now, in our 28 years of doing stuff, we've learned how to get that up to 90% acceptance. So we're doing great, but it still means that there are a number of projects where you've done some fantastic work, they thank you for it, they pay you for it, and they never use it. It's like being a chef and you're cleaning up and you've seen that they've scraped your customized, awesome meal into the trash. And so that's just not fun. People won't stay and work for you if their stuff's not implemented. Clients won't call you back, obviously, so we kind of need to see it through. And I see a secret for that is understanding something about cognitive biases. What are our predictable and mental flaws that keep us from doing the right thing, keep us from doing rational things? So those are the three things I want to talk about, and again, emphasizing that we have to master the technology to really add value, but we also have to be effective in what are called the soft skills of, dealing with those carbon-based life forms like humans. So, and not all of us, I'm extremely outgoing. Not everybody in this field is, and so you definitely want to be on a team where somebody can speak human and can translate to the other folks who don't have the same technical lens for seeing the world that we do. All right, so I want to talk first about ensembles. There are lots of different methods, decision trees being the most popular nonlinear method, nearest neighbors, and I'm showing the response surface of, in the nearest neighbor, whatever the known point is that you're closest to, you take their value. So it's kind of like that kid in junior high that was doing that, on your test. But anyway, if the surface is smooth, then that's a pretty reasonable approximation. So I'm just showing here a bunch of plateaus, depending on the location. You can have nonlinear differentiable things like neural nets or polynomial networks, kernel density estimation, and then I invented a technique I called the Launay triangles. It's a simplex in 2 dimensions. It'd be hinging triangles, estimating a smooth surface with sort of the facets of a diamond sort of thing. And that has a great advantage in that it also has a conditional, you have not only the estimate of the response based on the inputs, but you also have your confidence based on this model. So, which one's best? Which one should you use? A lot of the people have their favorite, and we did a comparison a while back of 5 of the most popular techniques on 6 interesting problems in the literature, 3 of which are real, 3 of which are made up, and the lower one is the better one. So can anybody see, it's a little hard to read from here, but can anybody see like what technique won overall out of this set of techniques? What color is lower most of the time? Neural networks, yeah. So neural networks didn't do well on the first problem, but they won or tied for the win on 4 out of 6. But if you look closely, every technique was first or second place at least twice. So every dog has its day. And I was in Chile when I gave this talk first, and there was a simultaneous translator into Spanish, and she said something completely different, didn't have any perros in there, and so I asked her later what it was, and she said, well, I put it in a local idiom. I said, tell the pig Christmas is coming. He said, the pig is like thinks it's all hot stuff, king of the barnyard. Well, Christmas is coming, there's going to be dinner. And I said, yeah, that's kind of the opposite of what I was saying, but it's the same idea, yeah, So anyway, so there's different problems have different characteristics, different solutions will work better. Well, ensembling, and this ensembling is just averaging the predictions of the 5 competing methods and making that a separate prediction. Look, it does just as well as the best method. And neural net doesn't always win. You don't always know which the best method is going to be. So this ensembling, if you have quality inputs, think of a fruit salad. You don't want any rotten fruit in it. But if you have quality fruit, more of it, the better. And the particular ensembling method doesn't matter as much. This is averaging, the green one there. So it beats, voting is the green one, averaging is the orange one. Voting is arguably better overall in terms of its overall characteristics. And then I had invented a couple of other methods that I was really excited about, and they only do a little bit better. So I'm less excited about it. So, the simple methods work well enough, and if you do need to get that extra performance, there's a couple more interesting methods. One of which is the best known is bagging, bootstrapped aggregating. Very good name by Leo Breiman. Leo, very inventive fellow. Unfortunately, he's passed away, but he's responsible for random forests, and originally had a lot to do with the CART algorithm and so forth. So lots of different things. The name matters a lot, though. He once had the product integrative method for probability likelihood estimation. And if you sound that out, it's PIMPLE. That didn't go very far for some reason. I don't know why. But anyway, bagging says, hey, sample the data, take random samples of the data, build models on those, and then put those vote those models together. So if we were trying to predict red versus blue here, you know, a decision tree is not going to do well. A decision tree says there, and that's a circle only a mother could love, you know. That's a great circle, Johnny, and putting it up on the fridge. Yeah, that's just not really a great circle because it's an Etch-a-Sketch. This decision tree only slices things north, south, east, west. But if you resample that a lot, then you get 100 different trees that have looked at slightly different versions of the data, and then cut it off at the 50-50 point, you get something that's a lot closer to the answer. And believe it or not, those 100 trees are less complex than the single tree. Now, they aren't less complex in terms of there's 100 of them, there's all these parameters and so forth, but it behaves less complex. So I've got a journal article on that I presented at the National Academy of Sciences because it helped to answer the question, why do ensembles work so well? Isn't Occam's razor that simplicity is better than complexity? Yes, but there's different kinds of complexity. And functional complexity is how flexible you are to arbitrary changes in the inputs, and ensembles reduce that flexibility. So it's like if you've ever been on a board of directors or a committee or something, the committee makes more cautious decisions because of trying to get consensus than a single person who's emperor for life would, you know, and not every decision is better, but they tend to be more cautious and therefore less flexible, more stable. So that's a real advantage of ensembles. Here's just one more picture, different lift charts. You can see the individual models all are a little kinky. That's technically the answer. But you put them together and you get smooth. And these are with decision trees, so the cut points are few in the original model, but they create a lot of intermediate cut points when you put them together in ensemble. So one last example, credit scoring, a real world problem. If you put one model together, that's the first column, two models together, three, and all the way down to 5, you can see that, especially if we just turn that into a box and whiskers chart, and the median performance gets better the more models you throw in there together, the more good models you throw in there together. So, you know, it's a new idea, relatively speaking, 20 years ago, but it actually wasn't, because if you look in ancient Near Eastern wisdom literature, it's been the idea of consulting a number of advisors before doing something that's been there for a long time. So, you know, there's nothing new under the sun. You're always just rediscovering things. So I wrote this up with a colleague, and show that in case you're interested in learning more. I want to move on now to target shuffling. Now this is kind of the newest thing, and you'll see why it's so important, because we have a crisis in science. This was the cover of The Economist several years ago. I was going through the airport in London. It caught my eye, picked it up, read it, and I was kind of astonished because it was talking about how severe the problem in science of reproducing results is. And I knew that we'd had that problem with some of our clients, and we developed a way to handle it, but I didn't realize how widespread the problem was until this, and also half the problem's been solved. This technique that we developed called target shuffling. So I'm kind of on a mission to talk about it as much as possible, because I really felt like it will make a very big difference in a lot of places. Let's see what the size of the problem is. A couple of these things come out of that article, a couple others I've added, but I've highlighted in red what the irreproducible percentage is. In other words, Lancet is a famous British medical journal. It only takes 1 out of 20 articles that are submitted to it, and of course people already pre-filter, you know, self-censor before they submit. In other words, not everybody would submit to there, but they themselves believe that only half of what they publish is true. They just don't know which half. It's kind of like marketing. I know my marketing is being wasted, I just don't know where. There's a famous medical science researcher, a doctor, PhD. I really need to meet him. He sounds like a great guy. John Ioannidis is a Greek-American. He estimates, and he's like the most quoted medical person of all time. You know, he's written a great article about how most scientific results are false, and he believes it's 90% that are there, and that's about what I believe as well. Amgen, when it tried to recreate 58 studies that it based its business on, could not recreate 90% of them could not replicate 90%. And we'll look at replication in a second. Bayer Healthcare, same thing. They were a little more successful. They only failed 75% of the time. And lastly, we'll look at an example where psychologists took the top 100 papers from a few years ago and were only able to replicate a third of them. And they failed 2/3 of the time. So let's look at that study. This won Science of the Year, Results of the Year for Science Magazine. The x-axis there is the original effect size. So the more impressive it was, the higher that x-axis. And then the y-axis is, 100 different teams, roughly speaking, tried to replicate those 100 different results, and that was the answer. So you should see that 45-degree angle line. That would be what you'd see with data scattered around that if things were as they were said to be. But in fact, the red dots are the ones that were considered not replicated, and they were about 2/3 of the results. You have the marginal distributions on the side there. Yes, question?
What is replication power?
So the size of the data set mostly, how strong the evidence is. So you might recognize a very high proportion, just like in the first one, but if you have a lot of data, that's got a lot of power. If you only have a little data, that's less significant. So the size of the dot is that. So most published results are positive. So just, well, we'll look at this next example here. This is what, you think of a paper as like a recipe. So there's this phenomena on Pinterest called nailed it, where somebody is not able to replicate a recipe. So, someone publishes and says, oh, you can create this beautiful little minion cake for your little kid's birthday, and you try it out, and it's just not the same, And what about these Easter peeps? Aren't they cute? And they just come out kind of horrifying. Or here's a great Christmas card idea, and it just doesn't seem to work when you try it, So anyway, this is kind of how I see research today. There's a lot of nailed it, kind of not replicating the result very well. And the main way behind it, xkcd has a comment for everything, right? The main way behind it is that people are using significance tests that were developed by geniuses 100 years ago before they had computers. If they had computers, I've even read that Pearson's work and others, they said if there was only some way we could try all different possibilities and see where this falls. And it's like, well, now we have a way. We have this little dim-witted but high-speed assistant called the computer that can try things out. And that's essentially what target shuffling is. But they created formulas to approximate what those simulations would do. And they're very tight assumptions under them and so forth. But they didn't account for people trying repeated things. So somebody says, jelly beans cause acne, the first results are no, and then they hypothesize. They don't give up, right? They're all-American ingenuity and hard work. They say, what about the color? And so they try the red, the green, the blue, the orange, the purple, the brown, the teal, and almost always it's no result. And then one place, there's a significant result. So the next day, the newspaper says, green jelly beans linked to acne, only 5% chance of coincidence. Well, the 5% chance of coincidence is true if you rolled the dice just once. So say you're playing D&D and you have a 20-sided die, right? What's the chance of getting a 20? If it's a fair die, 5%. So you get that and you think, whoa. Well, what if you were able to roll the dice 10 times, 20 times, 30 times and take your best result? The chance of getting it would go way down. If anybody plays Settlers of Catan, right? If you roll a 7, you got to throw away half your cards if you have too many. Well, it's a 1 out of 6 chance that a 7 for 2 dice will add up to a 7, right? But if you have 4 players around the table, it's over a 50% chance that it'll happen by the time it gets back around to you. So, the more players there are rolling the dice and taking the more likely something is to happen. And of course, in the experiments, everything is interesting in different ways, right? Well, there were 5 in a row, or they were all blue, or, so the interestingness can happen a lot of different ways, and people don't realize that they're doing multiple comparisons and using a one comparison test. So that's why most results, optimists think 50%, pessimists think 90% of published journal results in refereed good journals. We're not talking the ego journals that'll just publish anything. So this is pretty scary. Think about the billions of dollars wasted, lost. And every now and then there's true fraud. Recently there was the discovery that a very promising, very exciting anti-Alzheimer's approach was complete fraud. And for 10 years people have been spending billions of dollars and not confirming the results. So that is not what I'm talking about. That happens. It's kind of rare, but it's horrifying. What I'm talking about is inadvertent fraud from publishing a lucky result as if it were true. So how can you evaluate the luckiness of something? So we want to get into that real quick. Otherwise you get these spurious correlations. So if you've seen this before, we got to keep Nicolas Cage out of movies because lives are at stake, especially with pool accidents. Anyway, or the number of sociology doctorates awarded in the U.S. is eerily correlated with worldwide non-commercial space launches. So, if you look at enough variables and you don't have enough data to constrain it, you will find something that correlates just by chance. So how do we rein this in? Well, if anyone wants the slides, I'll give you a copy. I think the best way is to show you. Let's take an example of baseball. So these are the baseball strikes thrown one day in Major League Baseball, and that's the strike zone. So the height and the width of the zone of the plate, the height roughly from knees to armpits, and you're trying to hit the ball. Well, a hit is a hard thing to do, somewhat rare. It has to be inbounds, not caught. Nobody has to get out. You have to get on base safely. So the hits only happen about 9% of the time. On that day, they were the red dots. So the question is there a hot spot for hits? If you're pitching, you want to avoid that. You might be interested in the cold spot, the spot that's mostly blue, that's significantly blue, right? So how do you get significance? Well, let's break it into these little boxes and look at the proportions. So the proportion overall is 9%. The proportion in this little box is 15%. But the sample size is only 13. There's 2 hits and 11 knots. So the p-value takes into account the proportion and the sample size. And a p-value very close to 0 means, wow, we've got a significant rare event here. A p-value very close to 1 would be we have a significant non-rare event, so that would be mostly blue. That's harder to come by because extra red is easier to find than extra blue because extra blue is the natural state. So we just poke around in this and find some spots. This place is 1 out of 18, so this is 2 out of 5, so 40%. So that's appealing, but the sample size is so small that reduces the significance, but still it's almost publishable. In a medical journal, if you have a significance below 0.05, you get published, and this is 0.059. So you're like, so you might be tempted to move the box just a little bit, to get the right. I'm not kidding. That would be what a researcher would think of doing because I want to get this result significant. So, but the main thing is we're trying lots of different boxes, and the test was, what if you tried just this one spot? Okay, but instead we're rolling the dice 40 times when we do this. Now we run across a spot that looks really good, and spoiler alert, this is the winner. This is the best spot of all. It has a p-value of 1/3%. So really significant. But the point is, how easily could it be if we just randomize those points, how easily would we find something that's significant? Because there's always going to be a winner, right? You randomize the points, now you do the search again, one of them is going to catch your attention, and it's probably going to be publishable. But you know that it's false because you just randomized which ones were red. That's the key about target shuffling. So if we went through this and we found a bunch, we would settle on this one as the winner, as I predicted. I was right again. And we would publish it, right? Because it did such great. And that p-value, though, think of the p-value as an interestingness score. It's a probability if you do it one time, but not if you do it multiple times. So think of it as an interestingness score. So now what we're going to do is we're going to randomize. This is the original markings. Actually, that might be a randomized marking. Let's see. I'm trying to see if the dots change color. Yeah. So the dots have changed color. If you look at one of them on the original, focus on a red dot, and maybe it turned blue this time. So we shuffled, we left them in the same physical location, but shuffled which ones were red. Now, randomness is rule. There is no connection between the physical location in space of a pitch and whether it was hit or not in this new world we've created. All right? So we have the advantage of knowing that everything is luck in this world. But in this world, when we search on it, we find a best. And it has a p-value of 1.7%. So it's publishable, you know? So, and so we do it again and again. We try all sorts of different shufflings, research for the best one, and then record it in a histogram over here. The red line on that histogram is our original result. Things to the left of it are results better than our original. Randomized results that were more significant, scored higher, scored better. Ones to the right-hand side are worse. So when we do this 10, 20, 30, 100 times, and we'll stop at 1,000, we look at the proportion on the left, the proportion that were better. We ended up at about 18.4%. So roughly 1 out of 5 random results scored higher than our actual result. So that's the true significance. The significance is how likely could a random result score higher? And the answer is 18%, 20%, let's say. So you go back to the business person and you say, well, I did a bunch of simulation experiments, and there's a 4 out of 5 chance that this hotspot is real. What do you think the business owner is going to do with that, the business person, in this case, the coach or the manager? Okay, nothing. They're going to run with it. 4 out of 5? Are you kidding me? That's awesome in baseball. You know, that anything would have a 4 out of 5 chance. So this is one reason they've had to change the rules in baseball recently, because analytics was so successful at keeping people from hitting, and it was already a boring game. So, sorry. But it was already, and so they had to speed it up, and they had to, you know, anyway. So it's fascinating. Analytics has affected when they first did analytics in the National Basketball Association, they estimated that they were adding 2 points per game for the teams that used it. So it was enormously, that's very significant. Even though there's 100-point games, you know, that's very significant. So in our business applications, people will run with that. And they need to know, instinctively they know they can't believe the p-value, right? It's just completely wrong. But what we're doing is we're using the p-value as an interestingness metric and then calibrating it to a probability through experimentation. And then the probability is something that people can understand. Hey, I did a bunch of simulations, and this really proved powerful with our first big client that we had, 30 years ago. It was a hedge fund, and we had verified that a certain idea worked really well in the markets to make money, and he had thrown some toy money of his, $2 million, in on it, and I had thrown my entire life savings of $40,000, and my wife threw her entire life savings of $20,000, and we were all in. He was, and we made 40% the first year. It did great, but it was a very rocky ride with lots of scary ups and downs. It's kind of like riding a roller coaster in a third world country. It was like that was maybe too exciting. So. At the end, he didn't want to go forward, and I had to basically invent target shuffling to show him that, in that case, there was only a 1.5% chance that chance would have done better. And at that, he believed it. He had an MBA, he had an engineering degree, smart guy. I showed him p-values and all, he just, blah, blah, blah. But when I did the resampling experiment and showed him that, there was only a 1.5% chance that a random timing of the market would have done better than the timing we actually had. Then he put $20 million in and started to invite others in, and eventually we were running about $1/3 of $1 billion. So now he kept all the profits, but anyway, it was still a fun experience. and all. So I write up the target shuffling idea in this book, with our first book, and but at the time I didn't realize its significance. I kind of joke, I don't know if anybody's a Lord of the Rings fan, it was kind of like the ring in The Hobbit, you know, it was kind of this little thing, and then by the time the author wrote the rest of it, it had matured in his mind to being the one ring that rules them all, like the most important thing. And I kind of feel like this concept is really that. I had developed it for one thing, but then I realized that it's applicable to all of science verification, which is a crisis that needs solving. And the thing is, we have the tools to do it. So very exciting. Well, let me go on to the last one, cognitive biases. And in this one, I'm just a student watching what's going on. I have nothing to, I make the mistakes, but I haven't had nothing to do with the field. You know, if we're going to succeed, our stuff has to get used. And there are some necessary components to that. One is, of course, the mastery of the technique. We really need to know the data science. We need to know the kinds of ways it interacts with the real world and the problems that people can have. The problems there can be with the data, like, you know, survivor bias. You have the data, but you don't have all the data because, you know, let's say you're doing something, you're hiring people and you're evaluating resumes and then you're later correlating that or not. You only know of the people you hired which ones were successful and which ones weren't. You don't know about the ones that you didn't hire and didn't give a chance to unless you do some extraordinary following up with those, you know. And so there's most data problems are censored, or there's survivor bias. You know, people that didn't make it through that first filter, we don't know the rest of the story from them, and that can really affect things. So you need clear thinking to be able to try to shake those issues out. But there's also a piece that you have no control over, almost no control over, and that is things on the client side, the people who are going to use it. They need trust. They need, well, you can have some control over that. They need to trust you, and they need to trust the technology. And so, and it's best to work with them over time so that they have an opportunity to be a part of the solution. You don't want to be setting up a, you know, I don't know if you read old comic books and they have the before and after, the person gets sand kicked in their face or whatever, anyway, or the diet. You don't want to be like, okay, you're the before picture and I'm the new hotness, I'm the after. No, together you're going to create something better than before that you couldn't do without them and they couldn't do without you. So that's important. And then they have to have enough understanding of technology so that they don't panic as they're about to do it. Imagine, you know, who gets fired? The person who does something weird and wrong, right? But if you do what the herd does, you're not going to get fired. So doing something new, there's this terror people have, may not even be conscious, that they're going to pop their head up and get shot, you know, because they've done something weird and different that didn't work. And the risks are not there. If they do something that works, maybe they get a promotion, maybe they get a raise. If they do something that fails, maybe they get fired. And those are not symmetrical risks and rewards. Even if they were symmetrical, we humans are wired to fear loss much more than we appreciate gain. So, you know, we have to think about it from their perspective. Okay, so they have to be also willing to change now, change the way they're doing something, and the change management is really hard. Now, one thing, a great book from this is Daniel Kahneman's Thinking Fast and Slow, and Daniel Kahneman is a wonderful guy. There's a book been written about him and his collaboration with Amos Tversky. He ultimately won the Nobel Prize in Economics. Tversky would have also, but he had passed away, and they don't give posthumous prizes. But I've met Kahneman when he visited Charlottesville. Very, very fine fellow. And he's sort of in the lead on this concept of looking at the brain as a model of two systems. One being very fast and intuitive that we use almost all the time, and the other being slow and analytical and effortful. And that's the system you're going to be using today as you listen to all the speakers, and that's the system that we have to use to add value to our clients. And our clients are like a big brain. They don't want to think. They want to just react. They want to go with their gut. And it's worked pretty well for a lot of the managers. That's how they got where they are, right? So we're trying to get them to do something they don't want to do. And sometimes they learn to trust us and outsource this hard thinking, you know, but it's not their natural way of doing things. So that might seem strange to folks that are mostly technical and think, you know, and logically, but we're in the minority. So especially when people are in a good mood, they don't like to use their brain. You know, you can do a test on somebody. If you say, okay, 3 times 7, somebody can answer that just without even thinking. But 33 times 75, you know, you'll be like, wait a sec, and your vision will decrease, your hearing ability will go down, you'll be thinking about it. It's using calories, it's using effort. And then when you give the answer, you release. But that's exhausting if you were trying to do that all day long. So they can measure the dilation of your eyes to see if you're using system 1 or system 2 and do experiments and so forth. And it's fascinating. But it comes out in the real world in some very interesting ways. So there was an article in the National Academy of Sciences about parole hearings in Israel for people who, there's a compulsory military service there. Every citizen has to, and if somebody in the service acts up, they get put in the brig, and then they get a chance for parole, and there's the very, very high volume of cases. So the judges, there's 8 judges in the court are working in parallel. Each case takes about 6 minutes. That's how fast they're moving. They often have lawyers and the person present there. Things are moving fast. And about 1/3 of the applicants are approved for parole. Somebody did a time-based study of it to look at the 8 judges. They're all kind of acting in parallel again, and looked at the proportion of approvals as the day went on. And it was not flat. Now this should be a horrifying chart. There's something else going on here about approvals. And anybody have any idea what those humongous change points might be, the dotted lines? Lunch, yes. So whoever's speaking right before lunch, I'm sorry, you know, you're down there, and right after lunch, people are happy again. Yes?
Is who goes when by chance?
Not quite. There's some arguments against this by saying that they, so all ethnicities and cultures are in there. And there's some thought that some might have a higher proportion of disagreement with the Army than others and so forth. And there is some ordering that way because of geographical location and the way they do things. But that would explain a very small part of this. Yeah, these are incredibly dramatic. I don't know if that's a smoking break or these are bathroom breaks. The little, you know, what's going on there is obviously biological in some way. You know, like we are human creatures that need recharging, need breaks, need, you know, I don't know if you've run into this saying before, but I've seen it live. In my experience, is never go to a judge just before lunch. No, never be seen by a judge just before lunch. And this is literally that exact thing experimentalized. And I've seen that happen. A friend of mine was in the New York federal court review, you know, appealing the case, and we went to support him, and there were 3 cases, and it was, you know, and lunch, and the judges were getting more and more grumpy as time went. He had no hope. He ended up going to jail. So he's out now. But anyway, it was all a trumped up thing. It was not a real crime. It's amazing. So anyway, where is this happening to us? Right? Let's say we're the judge. And these judges are experts. They're doing their best. They're trying hard. They're exhausted at the end of the day from trying to give every case a fair shot, right? Well, we're the same way. Where is this happening to us? I did have a colleague. So we have offices in Linthicum here and in Arlington and Raleigh, North Carolina, and Charlottesville, worldwide headquarters in Charlottesville. You know, I was visiting our DC office, our Arlington office, and kind of reviewing projects. Normally I would go there, I would just am social or play a game or say hi to people. But this time I wanted to review projects and try to be helpful. And my colleague was dressed in a suit, and he was standing up, and I was having a hard time, after several projects, I was having a hard time understanding what he was conveying to me, a graph, and that was messing with my image of myself as a person who understands analytics stuff, you know, so I was kind of getting irritated, and then I saw him, he was shaking, you know, so here's one of my senior people just, and I'm like, okay, I remembered this chart. Let's go to lunch. And so we just dropped everything, we got outside, we got some tacos, we came back, and it all was so much better the second time around, you know, just so I at least one time caught myself. You know, but most of the times we're blind to this, and this is really scary. So I think we need other people to speak into our lives to help us find this. Anchoring, I'll just talk about 2 more cognitive biases in my last few minutes. Anchoring is a big one. Here's a shoplifter in Germany. This is the judge. I lived in Germany in my kindergarten year, and I saw a lot of faces like this. So I know it's an American judge, but it just reminded me of, because there are a lot of rules in Germany. There's rules about most everything, so, and I found a way to violate them, I guess. But anyway, the judges are reviewing the shoplifting cases. And the experimenter has gotten permission to say, okay, we're going to do this little thing. Don't let it bother you. Rolls of these dice. So the dice are set to be either a 3 or a 9. They're weighted dice, okay? So right before the person is supposed to cognitively figure out the sentence for the offender, they have to look at these dice, and then they do it. If the dice has a 3, the average sentence was 5 months. With a 9, the average sentence was 8 months. Should have absolutely no effect on it. You know, so the effect size of the dice was half the sentence was due to the dice roll on average. Really scary. You know, a lot of times people will anchor, how much is this house worth? Oh, it's this. Oh, I don't know anything about it. But at least that number's been thrown out there. So if you're negotiating for a raise or something, get the conversation talking about the national debt or the number of fish in the sea, or, you know, just get those numbers way up there. Anyway, this is amazing. And I think it's partly because we, you know, back when we were tribes, small tribes of people trying to survive in the wilderness, you know, you didn't really want to disagree with people a lot. You didn't want to get voted off the island. That would be no more survival for you, you know. So I think we would just are wired to like start with what somebody else said and modify it a little bit, you know, rather than trying to think afresh about it. And even when that makes no sense, like dice, we're kind of like not offending the dice in some weird primal way. So we have to force ourselves to think about things from scratch and not fall prey to that normal bias that we have of letting something else affect us. Last one, the halo effect. This can be for good or for ill. This is a phone booth in New York City. Now, some of you younger people may not recognize that, but think of it as a quiet space with a tethered cell phone. You know, so what would happen is people would use it, and then just after they use it, the researcher would walk by and spill some papers. Now, New York City, big city, how many people helped that person out with those papers as they were stepping out of the phone booth? None. That's a great first approximation. The answer was 4%. And my New York City friends say, oh, they weren't from around here. So 4% help. Now, they make one small change to the experiment, and it's not having a more attractive person drop the papers or the papers turning, you know, colors or whatever. They make one more change to the experiment, and and 88% of people help stepping out of there. So 20 times as many, roughly, people help. And the change to the experiment was a dime was left on the shelf prior to the person entering there. So they had a free phone call. This at the time, it was just a dime for a local call. So they did their drug deal or whatever, they step out, and now they're 20 times more likely to help that person pick up because of that dime. So when you go out here and you get a free T-shirt or a free squeeze toy, you know, yeah, they're using that, and it's good, but it's irrational, right? Are you gonna work for a company because of the free T-shirt? Yes, if it's Boeing, right? No, but anyway, no, I don't mean to. But it's just, you know, we get affected by that, or you feel a sense of reciprocity, and so you see that happen, and it's natural. It's part of our natural bias. But is it logical? So those are there. And helping to understand some of those natural ways, especially people's fear of change, is, I think, very helpful for actually implementing things and helping them, jump over that hurdle. So to conclude, I'll just say, these are breakthroughs. Really, these are actually lessons in humility. Ensembles tell you we can't do it alone. We really need alternative perspectives. Target shuffling says some of what looks like skill is really luck. So can we measure that and get the true generality? Then we'll be much more confident in our results. And cognitive biases says we ourselves, as well as other people around us, are making mistakes right now that we're blind to. Again, it helps to have other people around who have the willingness and ability to speak truth to you and help you figure it out. And what we're doing is extremely valuable. I love this far side. Hey, look what Zog do. So Zog has invented the technology of the stick, and he is burning his rat without burning his hands. And the normal way of doing it has pretty obvious flaws. It's interesting that the glasses technology preceded the stick technology. But anyway, so Zog has this thing that's going to really help the tribe out, this new technology. But you'll notice that Zog eats alone. So what happens next? Is Zog going to be able to have impact on the people around him? A colleague of mine says, here you have the inventor, you have the early adopters, the one that's looking, you have kind of the loyal follower, and then you have the guy that's going to do it the old way no matter what. He's going to, this is the client, yeah, this is the way it is. So they'll never adopt the new technology. But anyway, just a reminder, if we're going to have an effect, we have to bring other people into it. We have to be able to communicate that. So best of luck to you all. Thank you.
Hello? Oh, there it is. John, do you mind answering some questions?
Sure, be happy to. I just want to.
We have our mic stand right here. If you'd like to come ask John a question. That was a lovely talk.
Sorry to take a little extra time.
Thank you for your talk. In the method that you were using for the p-values, when you were talking about reproducibility and you were using the boxes, I had two questions. One was, how did you, when you drew the box, how did you calculate that p-value? Like you had one where it was like you had the proportion of hits, or number of hits, number of strikes, and then the proportion,
right.
And then you had the p-value. And then my second question is, so I work at in epidemiology, and one of the things that they're trying to do is to move away from p-values and move towards something like standardized mean differences. Could that method that you're using also be applied to standardized mean differences?
Yes, so the method just needs the p-value is just a little formula that takes into account the sample size and proportion of the full population and a sample size and proportion of redness of the small population, and then says, what's the likelihood that, think of it as urns, statisticians love urns and balls. If there was a bunch of red balls and blue balls of that proportionate size and you were to draw out a sample of a certain size, how likely would it be this particular configuration of reds and blues? So that's just a mathematical formula that's normal. And if that were the only experiment you're doing, that would tell you the significance of your hypothesis. I hypothesize that it's green jelly beans or whatever. Then you do this sample, and if that's your one hypothesis, that's equal to a probability. But if you do multiple hypotheses, if you were saying I'm gonna roll the dice 20 times and I'm gonna take the best, that's a different distribution than the distribution of one roll. So what target shuffling does is it says, let's do a bunch of experiments where we know the results. There's no relationship between the inputs and outputs because we've shuffled the outputs and assigned them to different people, in this case the redness. So in that null hypothesis world, we get this distribution of results that are available by chance, and our result is here on the distribution. The area is only 18%, that's better. So it can work with any measure of quality. The p-value is just a measure of quality. The problem is that people are using the p-value as if they had thought of that original. They do a big search and they find something interesting. And then they said, what if I had thought of that interestingness thing at first, oh, here's its p-value. And that's not honest.
That's like p-value phishing almost? Or?
Yes.
Okay.
So p-hacking, it's called sometimes. Yeah.
Right.
And so p-values are great, but using them as if they are the significance. They're a measure of interestingness. And what you have to do is calibrate the measure of interestingness to significance. And that would be a problem with any measure of interest that you have that you're doing a search over. Again, think of it as I'm rolling the dice. Every search that I do, everything I try is a roll of the dice. So you have to take that into account.
Okay, thank you.
First of all, thank you so much for such a fantastic talk. I'm looking at the first part of your talk after hearing the second part of your talk. And what I'm thinking is, in the second part, you were saying, hey, if I sample enough, in the end, I might find something interesting, right? What if I keep on trying like different ensembles, right? Or I try different combinations of ensembles, right? Wouldn't you face a similar issue where you might find something that works kind of well? And
grab this thing back. No, great point. And I'm not being shown because the next one's outside. I'll just remind you because I don't want to take too much time. So if you remember, I showed a credit scoring problem. And there was 5 different techniques. So there was 5 different ones, got different accuracy, lower being better. And then if you combine them in pairs, there's 10 different pairs, 10 different 3, 5 different 4, and only 1 5. So there was if you did that, you could cherry pick and say, oh, there's this great result here where I combined the 3 network methods.
true.
And I was avoiding that and saying, the general trend is that it's getting better. And actually, we've gone out to combining as many as a dozen methods and so forth. And that continues. You never overfit because it's independent models that aren't looking at each other being combined together. And it turns out that it pretty much goes down and never comes back up with the number. So you're right, that would be a problem. If I cherry picked and said, well, I've done these, 32 experiments, or is that about right? Yeah, 32 experiments, and this combination of 3 is the best. That's cherry picking, and that would fall prey to that. But you can instead you can say look at the general trend, and so I recommend in most cases. But that's the reason ensembles don't always win. They just usually do. So, yeah, it's very rare in statistics when you can say something is always true. So far, I'll end with one thing that I've found so far that's always true. So this is a challenge to you. So far, I have found that an ensemble of trees always has beaten a single tree out of sample. That's pretty amazing. Not that an ensemble tree is always the best by any means, or ensembles of other things, but with trees alone, they are particularly improved by ensembles. Yeah.
All right, thank you so much.
All right, thank you all very much.